Hello viewers, welcome you all. In today's lecture, I am going to start new course of physics and the course is electronics, right? Electronics. Now, as I have told you that electronics play a very important role in all competitive exams, right? And the equal number of questions are asked from electronics as are asked from nuclear and particle physics or solid state physics. So these three courses I have already told you that these are very important in physics. So today I am going to start the electronics course. We know very well that in electronics also we have two different branches. One is analog electronics and one is digital electronics, right? So these are the two branches, separate branches of electronics. So today I am going to start with the digital electronics, right? Digital electronics. So now you know very well that in digital electronics the digital signals are used, and digital signals are discrete signals. They are not continuously time varying signals. We are using only certain reference levels for representing a signal, right? And we know very well that in digital electronics the number system plays a very important role, right? And usually questions are asked from the number system. You can see all exams, right? Question are asked from the number system, whether it is for the conversion of one base to another base, or you can be given a problem where you will be given addition of two numbers, subtraction of two numbers, right? But these numbers will be in the number systems that are used in digital electronics, right? So here today I will talk about in details about the number systems and base conversions in digital electronics, right? So what is a number system? First of all, the question is, what is a number system? So number system is basically a way of representing the given number by using some discrete digits or symbols. The requirement is the digits that we are using, they should be unique or discrete, right? They should not be same, right? We are using unique digits or symbol for representing any number in that number system. So the most commonly used and discussed number system that we all know, it is the decimal number system, right? That is a standard number system that is used for day-to-day calculations, counting, right? So it is decimal number system. But beside to decimal number system, we have some other number system that are used in digital electronics. So I am writing the number systems that are commonly used in digital electronics. So they are binary number system, right? The second one is octal number system. Then third one is decimal, and the last one is hexadecimal, right? So these are the different number systems, right? These are the number systems that are commonly used, right? So I will start with the first one, that is binary number system, right? I told you what is number system. Now what is base, right? Base of a number system. The base of the number system define or tell us the number of unique digits used for representing different numbers, right? So obviously in decimal number system we have 10 unique digits, right from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are in total 10 unique digits. So decimal number system has a base of 10, right? So we are familiar with it. So I am writing down all the bases and the unique digits for all these number systems. You can see here I am starting with the binary. Binary number system is the commonly used number system in digital electronics. So in binary number system, we are using only two digits, 0 and 1. These two digits are also known as a bit, right? Bit is written for a binary digit, either 0 or a 1, right? If I have a combination of 4 bits, I mean 0 1 0 1, then the combination of 4 bits is known as a nibble, right? If I have a combination of 8, right, like that, I am taking any example, right? Then this combination of 8 bits is known as a byte, right? So you can be asked a question that what is a bit, what is a nibble, what is a byte, right? So this is associated with the binary digits and binary number system. Now look at the binary number system. What will be the base of this number system will be 2. Why? Because we are using only two digits, 0 and 1, right? So base is 2, and any number in this number system will be represented as a combination of 0 and 1s, right? Now I am coming to the second one, right? Octal number system, right? So if I come to the octal means 8. We are using 8 unique digits, 0, 1, 2, 3, 4, 5, 6, 7. These are 8 numbers, unique numbers that are used for representing any number in the number system, right? So obviously its base is a base 8, right? So it has base 8. Similarly, if I come to the decimal, I already told you that the decimal number system is the commonly used number system, and the number of digits, unique digits, they are 10. The base is 10, right? Now I am coming to the hexadecimal. So in hexadecimal, we have 16 unique digits. They include 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, F. So these are the total 16 unique digits or symbols, right, that are used for representing a number in hexadecimal number system, right? And its base is 16, right? So this is about the base and the number system, different number systems that are used in digital electronics. Now I will come to the conversion, interconversions, because question is asked. You can be asked that convert the given binary number into decimal number, convert the given decimal number into octal number, or it can be anything, hexadecimal to octal, hexadecimal to decimal, right, binary to hexadecimal. So these type of questions are usually asked. So I am starting with the binary, right? Suppose I am giving a binary number and I have to convert it into the corresponding decimal number. So I have to learn the process how I can convert the given decimal number, right? Because decimal number is the commonly used number, to binary. First of all, we should know it, right? So when I want to convert a decimal number into corresponding binary number, right? So for that, I am going to use a method that is known as a double table method. Double table method. Double table the method means I am going to divide, right, the number by 2, and I will keep on dividing the quotient till the quotient becomes 0, and I will keep on recording the remainder. Then I will read the reminders from bottom to top. That will be the given binary number. Let's take the case of 12, right? So if I have 12, right, then I am dividing it by 2. So what I got? I got 6, right? In the next step, I got 2 6 12, 2 6 12, remainder 0. Then again 2 3, right? 2 3 6, remainder 0, right? Then again what is 2? Now 2 banja 2, right? 2 banja 2, right? And remainder 0, right? Now here, sorry, not remainder 0, 2 1 2, remainder 1, right? I mistaken here. 2 banja 2. It is 2 banja 2, right? So 2 banja 2 plus 1, so remainder 1. Now again now 1, it is not possible. So 2 into, now the quotient is 0, 2 0 0, remainder 1. So this is the way, right? Now we reached at quotient 0, right? So when we reached quotient 0, we have to stop. Now we have to read this number that I got here by recording the reminders from bottom to top. So the number is 1 1 0 0, and it will be written in bracket base 2, right? That this 2 represent that this number is in the binary number system. So this is the corresponding of 12, that is represented in decimal number system to binary number system. So this is the way of converting a given decimal number into binary number, right? Now if I want to do vice versa, I want to convert a binary number into the corresponding decimal number, right? So for that, let's take the case 1 1 0 0, right? So now in this number system, I have to represent each bit position by the power of 2, like 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, right? So each, the place value of each digit in this number system is taken as the power of 2 starting from 0, right? We are doing the same thing in decimal number system when we are writing the place values. You take the case of, for example, 23, right? So what is the place value of 3? 10 raised to power 0. What is the place value of 2? 10 raised to power 1, right? So when you solve it, 10 raised to power 0 means 1 multiplied by 3 plus 10 multiplied by 2. You got the same number, 23. So this is the same thing that we are doing here, right? 2 raised to power 0 multiply with this, 2 raised to power 1 multiply. So in all number systems, when we are converting that number system into another, we are taking the place values in the power of the base. The base is 2. So here the number will become 0 0, 2 raised to power 2 4, and 2 raised to power 3 8, 8 plus 4 12. So this is the way of converting a given binary number into decimal number, right? Now it was a very simple case. Now suppose I am giving a number that contain a fractional part. For example, let it was 12.21, right? In that case, how I will convert? First of all, I will convert this part, integer part, and this is represented as a 1100. Then I will play decimal. Now I will convert this 0.21. So the way is to multiply it with 2 and record the integral part. So when I will multiply it with 2, I will get 24 point, right? The integral part is still 0. Then 0.42 multiplied by 2, then I will get 8. Still integral part is 0. Then 0.84 multiplied by 2. Now what I get? I get 1.68. Now the integral part is 1, right? Then read downward from top to bottom, that is 0 0 1. Now this is the required number corresponding to this number in base 2. So this is the way of converting fractional part in the corresponding binary number system. Now the process will be reversed if I want to convert this number back into this one. How? I told you to convert this number into this one, how we can calculate this number to 12. Now similarly for this one, what I will do? I will start from this position, but 2 raised to power minus 1, 2 raised to power minus 2, 2 raised to power minus 3. And toward this side, 2 raised to power 0. So I have done this one already. So if I do it, then 1 by 2 multiplied by 0 plus 1 by 4 multiplied by 0 plus 1 by 8 multiplied by 1. So I got 1 by 8. So 1 by 8, right? What I will get? So when I divide it, so 8 1s are 8, 8 2, 8 2. So I got approximately this. Now you will get exactly the same number that is taken here. If you increase the number of divisions here, then you will reach at the exact value of this fractional part. Otherwise you will get only approximated value, right? So in that case, you won't be able to generate the exact value of the fractional part, because for doing that you have to increase the, these divisions, right? Sorry, multiplications. So this is the way of converting decimal into binary, binary into back decimal, right? Now the same process is done for octal number system, right? But the thing that is different, right? I'm taking the octal, second part, octal number system. Octal. In octal, you know very well 0, 1, 2, 3, 4, 5, 6, 7. We are using 8 unique digits. So when I want to convert, for example, 12 into corresponding octal number, 12 is in base 10. So what I will do? I will use the octal devil method. Octal devil method. Octal devil means now I will divide it by 8, right? So 12, the process is same. Divide it by 8. So 8 banja 8 4 12, right? Then now again by 8, right? So 0 and here remainder is 1. So then what is the answer? Answer is 1 4 base 8, right? So this is the correspondent of this number, right? So you can see here the conversion from a decimal to octal, right? Now if you want to do the reverse process, then again the rule is same. We have to multiply it with the place value, but place value in this case it will be the power of 8 because the base is 8. So 8 raised to power 0, 8 raised to power 1. So 8 raised to power 0, 1, 1 into 4 plus 8 into 1, 8 into 1. So it is 12, right? 12. So the same thing here. So this is the way of converting from decimal to octal or octal to decimal, right? Same rule is followed for the fractional part. If it were 12.21, then 12 is represented as this. But about 21, so for 21, 0.21 multiply with 8 and record the integral part, right? So 8 to the 16. So 1.6, right? So here the part is 1, right? Then 0.68 multiplied by 8, right? So again, when you multiply 8 is 64. This one, right? So now it is 5. Then 0.44. We have to consider only the fractional part into 8, right? So this is the 0.153 and 14, right? So this is the required number corresponding to this number in octal number system, right? This is the number corresponding to octal number system. So if you want to convert this number into back into this one, what we will do? Again the same rule. We have converted already this into 12, but about this again 8 power minus 1, 8 power minus 2, 8 power minus 3. So you take multiplication 1 by 8 plus 5 divided by 64 plus 3 divided by 64 into 8, 8 power 3. So this, when you will simplify it, you will get an approximation of this, right? I told you, as you increase the number of multiplications, you will get the closest value to this. Sometimes you can get the exact value, but it is not true that always you get the same, but the rule is same. So this is the rule for conversion octal to decimal and decimal to octal. Now I am going for a hexadecimal, right? Hexadecimal, number to decimal. So in hexadecimal, hexadecimal number system, we know very well in hexadecimal we are using 16, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and the base is 16, right? So you can be asked that you convert the given number, right, for example, decimal number, right? Now we are not going to take 12 because it is already 16. So let take 21. So I am giving 21 in base 10, that is decimal number system, and I am asked to convert it into this number system, base 16, right? So base 16 means now I have to use the hexadecimal Deval method, right? I mean, I have to divide 21 by 16, right? And then record the quotient. So 16 banja 60, 16 and 21 means 5 remainder. Then again 16 0 because 1 is not divisible. So 0. So here remainder is 1. So what is the corresponding number? 1, 5 and base 16. This is a number required, right? Now if I want to convert back it here, what is the process? Same process, place value. So 1, 5, 16 power 0, 1, 16 power 1, right? So obviously it is 16 plus 5, it is 21. And again, if you have a fractional part, the same rule is that is followed here and here. What you will do, suppose it was 21.21. So what you will do, 0.21 multiplied by 16, right? So whatever you get, 16 1 is 16, right? 33, right? So you will record it with the integral part 3, then 0.36 multiplied by 16. You will keep on doing it, and again you will, whatever number you will get here, you will record that. That number will be representing the fractional part in the same way as you did for octal number and binary number system. So these were very simple conversions of a decimal to binary, binary to decimal, octal to decimal, decimal to octal, decimal to hexadecimal, hexadecimal to decimal. But now you can be asked a question, right, that you will given a number, right? I mean octal number, right? Suppose I have given an octal number, that is 36, that it is an octal number in base 8. Now if I am asked to convert this given number into corresponding binary number, right, or base 2, then there are two ways of doing it. One is taking the division method, but as the this number is going to become high and high, then the division will go on increasing, right? And the steps in the division will increase, and that will make this entire process very complex. So to avoid the long divisions, there is a rule that I can use for directly converting a octal number into binary number or binary number into octal number. That method is to represent these number in its corresponding binary bit, right? We know very well octal number. Octal means 8, right? 0 to 7. If I write the binary numbers corresponding to 0 to 7, 0, 0, 0, 0, 0, 1, right? This corresponds to 0, this corresponds to 1, 0, 1, 0, 0, 1, 1, right? Then 1, 0, 0, 1, 0, 1, then you have 1, 1, 0, and then 1, 1, 1. This is 1, 2, 3, 4, 5, 6, 7. Now, if I go further, then the number of bits required will increase and it will become 1, 0, 0, 0, that is 8. But I am using only up to 7, right? So up to 7, how many bits are required? 3, combination of 3. It means I have to represent these values 3 and 6 in their corresponding binary, formats. So 3 corresponds to what? 3 corresponds to 0, 1, 1, and 6 corresponds to what? 1, 1, 0, 1, 1, 0. So this is the corresponding number. Ignore 0. So 1, 1, 1, 1, 0. This is the corresponding number. Binary corresponding number correspond to this octal number system. You can check it if you want to check it. that what is the number, binary number corresponding to this octal number system, right? Otherwise, what you have to do, you have to take the divisions, or you have to first of all convert this octal number into decimal number, right? Right? Then that decimal number will be further converted into binary number, right? And that decimal number will be a large number, right? That process, if you follow that process, right, then that process will become very lengthy. So to avoid this process, I can directly use, but the thing I have to remember, place value, so number of bits. In case of octal, 3-bit positions. So I am going to represent each octal number by its corresponding 3 bits. Then combine these, and this is the required binary number in a base 2 corresponding to this octal number given, right? Otherwise, the process is very tedious. Now, the same logic can be applied if I have been given a hexadecimal number. But first, I want to tell you, if you are given, suppose, a number 0, 1, 1, 0, 0, 2, not 2, sorry, how I can use 2, 1, 1, 1. This is the given number, right, in base 2. And I am asked to convert this number into base 8, right? Now, how I can do it? Again, there are 2 ways. One is, first of all, convert this number into corresponding decimal by taking the place values. Then convert that decimal number into corresponding octal by taking the division, octal table. But that is a lengthy process, right? That will waste the time. You can directly use this technique, but you have to start from here, these bits, and you have to start from the right side toward this side by taking the combination of 3, 1 to 3, 1 to 3. Now here only 2 are left, so I will place a 0. Nothing wrong in it. This one. Now these 3 a combination are formed 0, 1, 0. So 0, 1, 0 corresponds to what? 2. 1, 0, 0 corresponds to 4, right? And 1, 1, 1 corresponds to 7. So the given number is 247 in a octal number system. 247, right? This is the given number corresponding to this one, right? So this is the way of converting. You have to now take the combination of or group of 3 digits, 3 bits, starting from the right toward the left side. If you get less bits in the at the this side, you can place the zeros as you are required, right? That is not going to change the number. So this is the base. Now the same logic can be applied for a hexadecimal to binary conversion. Suppose you are given a hexadecimal number, that is 3ADE, and you are asked to convert. Now obviously it is a large number, it is in base 16, and you are asked to convert into corresponding binary, right? Now what is the way of converting it into the binary? Now here we are using 16 bits, not 16 but 16 unique digits, right? 0 to 9 and A to F. So 16 means I have to now go further. 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, then 1, 1, 0, 1, then 1, 1, 1, 0, then 1, 1, 1, 1. Count. It is 9, 10, 11, 12, 13, 14, 15. It makes the total 16, right? So what does it mean? If I go to 16, then again one bit will be added. I mean, now I require 5. 1, 0, 0, 0, 0. So 5 bits are now required for representing 16. It means up to 15 I have to use 4-bit positions. So the same logic is there. Now I have to replace all these by 4-bit positions, right? Starting from 0, 0, 0. Nothing wrong in placing 0 here. 0, 0, 0, right? You can see. So we are now taking the combination of 4 bits, right? So you can represent their corresponding. 3 means you can see here 0, 0, 1, 1. A means A will be corresponds to this A, B, C, D, E, F. So A means 10 and 10 is represented as 1010. 1010. What is D? 13. 1101. 1101. What is E? 14. 1110. Ignore these two zeros. 111011011110. This is the corresponding number in base to that correspond to this one. So this is the way of converting hexadecimal number directly to the binary number, avoiding the lengthy route of first conversion into decimal and then conversion into a corresponding binary, right? If I have the reverse process, same way, right? You are given group of these binary numbers and you are asked to convert it into base 16. What I have to do? Again, you have to take the group of these 4 bits. So starting from right toward this side. So 1, 2, 3, 4. 1, 1, 2, 3, 4. 2, 1, 2, 3, 4. This. Now 2 bits are left. 0, 0. You will again arrive at the same thing, right? Then look at these combinations, right? So I suggest you to at least remember this binary counting up to 16 by using 4 bits positions, right? Then you will be able to, if you have remembered these 16 binary formats of decimal numbers, then you will be able to solve these conversions very fastly. Otherwise it will take time. So this is the way of converting a hexadecimal number into corresponding binary number and binary number into corresponding hexadecimal number in in a very simple and a smart way rather than following the lengthy process. So this is about the 3 number system. Rather there were 4, but the 3 number systems, that is binary, octal and hexadecimal, they are commonly used in the digital electronics, and decimal number system is used in all daily calculations and countings. So I explained all the questions related to it. Now, sometime examiner can ask you to confuse you that he has invented a new number system, right? Suppose, right? And that number system contains 5 unique digits starting from 0, 1, 2, 3, 4. This is the new number system that examiner said he has invented, right? He is using 5 numbers, 0, 1, 2, 3, 4. So they are 5, right? Now he is asking you, please write down the counting in this number up to decimal position 10. I mean 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if he asks you to write down the counting in this number system, what is the counting? Of course, in this number system. Now I am writing in this number system. So it will become 0, 1, 2, 3, 4. Now up to 4, the things are same. But then what about 5? I will write 5 as 1, 0. Then 1, 1, 1, 2, 1, 3, 1, 4. Then I can't go to the 1, 5. 5 is not allowed. Then 2, 0. This is the way. He can ask you that write the bit the number corresponding to decimal 10 in this number system. So this is the way. You can do it by simply taking the concept of place values, but this is the way of converting it, right? So these type of questions are also asked in different competitive exams to confuse you. So if you know what is the basic process in these number systems, then you will be able to solve all these problems, right? So this is about the number system and base conversions. Base conversions means we are going from one base to another. Base 2 to base 10, base 10 to base 2, base 2 to base 8, right? All these things, right? So thank you very much.